back on track. I realized I showed your video, so I didn't want to have to deal with cutting that off. All right, so welcome to class 6, and today we're going to talk about the muddiest points from class 5, and then finish up part 5. So we didn't quite get through all part 5, and I want to finish up about joining and pivoting and all of that. And then I have part 6 is up on Dropbox. We'll see how far we get into that. It's quite long. It's really long. So I have a feeling that it's going to take up most of next class as well, just to see how far we get. So if you didn't see this, I added a video about reshaping from Dr. Kelly Bodwin. She's at, I think, Cal Poly, San Luis Obispo maybe. And so she has a nice kind of brief video talking about pivot longer and pivot wider. So if you want more, like another explanation of that, I recommend it. I think it's like 10 minutes long. So muddiest points. I guess before we get started, are there actually any questions that I should answer first? Doesn't look like it. So last time I very quickly went through an example. Well, so I first used case when, and then I showed you an alternative way of doing that with fact other and fact collapse from the 4 cats package. And I went through it pretty quickly, so I totally understand that there's some people that call that out as being a muddy point. And so I do want to kind of graphically show this. So if you remember, we had our cigarettes per day variable in our smoking data set, and I wanted you to make it into a 3 categorical factor, which was, I think, no cigarettes, 0 to 10 cigarettes, and greater than 10 cigarettes. And that we did with case when. And then I showed how to do that with the factor functions. And so I drew a little picture here to show you what I was doing. We'll talk more about factors versus characters today. Hopefully we get to it in part 6, or at least next week, just so you can see like why you would want a factor vector. We haven't totally explored that. But for now, just as an alternative and how to use these functions, what we started out with was this character vector. So it had all of these categories. It was a character vector with these options, essentially, all about how many cigarettes per day they smoked in the last 30 days. And there were some missing values. And so to do this kind of collapsing into 3 categories the factor way, I first converted it to a factor using as.factor. So that was like step 0, basically. And then I used fact other. And so fact other collapses all the categories that you don't specifically call out. I said there's an argument keep, and I said keep did not smoke. I said keep 11 to 20 cigarettes and keep more than 20 cigarettes. And so fact other saw those 3 as keeps and collapsed everything else into the other category, which I designated to be called 0 to 10 in quotes. And so that means I didn't have to type out all of these 4 categories. So I saved a tiny bit of typing there by like only specifically writing out those 3. So you can imagine if you have many categories, that fact other can be really useful if you want to just lump all of those together. So we saw a fact function of the week, fact lump, which is fact lump and all its variants, which collapses a bunch of categories into one. And this does the same kind of thing, except just collapses everything you don't specifically name. So now once after this step, we're down to 1, 2, 3, 4 categories, 4 factor levels, which is do not smoke, 11 to 12, more than 20, and 0 to 10. And then on top of that, step 2, I used fact collapse, which collapses levels that you name. It also is a way to rename or re-level, or you might say recode factor levels, because I told it that I wanted to essentially collapse, but not really collapsing, did not smoke cigarettes into the category none. And so that created a factor level none, which matched up with that one old factor. And then I said, I want to make another factor category greater than 10, which I collapsed because I told it I wanted that to include 11 to 20 and more than 20. So after step 2, we now have 3 categories, none, 0 to 10, and greater than 10, which is what we wanted. And I kind of drew that down here. and the NAs were all preserved. So that's one nice thing. If you remember when we were using case when, I showed you that you need to specifically use NA as a category. So we said something like is.NA cigarettes per day, then tilde NA, make it NA. You just have to be careful about that, but factors take care of NAs automatically, which is nice. So this is in part 5, the code. If you want to go back and look at the code to see how that matches up to this drawing. And I'll try to use these functions again, just to give you a little more examples. We could have done the whole thing in fact collapse. I could have said, skipped fact other and said fact collapse, this category equals none. These 4 categories, I'd have to spell them out. I'd have to say less than 1 cigarette, 2 to 5 cigarettes, 6 to 10 cigarettes equals other. Not other, but equals 0 to 10. And then I could have said, then make these 2 groupings together into greater than 10. I mostly just use that as like just to show you if you have a lot of categories you don't want to type out, the other is really nice to just lump them all together. All right, so the other thing I went through really fast was this kind of random if else example that I used. And I haven't really explained what if else is, mainly because I feel like case when covers all your bases. You might as well just use case when if you know how to use it. But because I learned if else first, I tend to use that as a slightly simpler version of case when you only have 2 options. So what if else does is it's a function that takes 3 arguments. The first is going to be essentially your Boolean test. So a true false statement. The second is going to be the outputted value if that test is true. And the second is going to be the outputted value if that test is false. So a really simple example, here's a simple test, 1 equals 2. That of course is false. So this is a Boolean test condition. And so I'm going to say if else 1 equals 2, give this character string math is wrong if this test is true, and math is right if this test is false. And because it's false, I get the second option, math is right. If I change my test, now this test is 1 equals 1, which is going to give me a true Boolean result. That means I get the first option, math is wrong. So it just toggles back and forth between the true value and the false value. So if this, then that, basically, if else, if this, else that is really what it's doing. And so you can do that, it's a vectorized function, and you can do that in a vector, which is what I was doing because I was using it within mutate. And so let's say we just have this short, simple vector, 1, 2, NA, and just to show you what happens with missing values. And so I use this true false statement is.na my vex. And so that's going along each element of the vector. It's checking number 1, it's checking number 2, and it's checking NA. And for any value that it is NA, it's going to give me the output missing string. And if it's not NA, it's going to give me the not missing string. So the true value and the false value. And so we get this result, not missing, not missing, missing, which is what we would expect because the last one, the third one, is missing and the other 2 are not, or they're equal to NA. And so similar idea, if I use the test my vec equals 2, so that means it's going to be true for the second one, false for the first one, and then NA actually for the third one. So that's what we get. Not 2, which is what the value I specified for false, 2, which is the value I specified for true. And then when it finds an NA, if it can't evaluate that statement, because it's missing, it can't come up with a true false result, it actually comes up with an NA, then you get another NA out of it. So if else does take care of your NAs kind of by default as well, which is nice. And so just as a kind of a comment that this is giving you a vector. So let's save it as something, let's call it new vec. So now we have this vector of length 3, it's a character vector, new vec. And so I could use that for something else later if I wanted. So the same idea is if we are just looking at a data set, I made a tiny version of the MT cars data just so you could see it. Here's my data frame, my tibble. Actually, I guess it's just a data frame. And if I want to use if else inside a mutate statement, I can do that. So my data mutate. So I'm making a new column. I'm calling it sil6. And I'm basing it off this column SIL. And so cylinders, number of cylinders in the car is 664,686. And so I'm running along that column, each row, looking at each row's value, and I'm saying this test. If else, if SIL equals 6, then give that value. If SIL equals 6 is false, then give that value. And so it's made this new column, SIL 6 over here at the end, and you can see when it's 6, I get SIL is 6 because that was what I told it to do. And otherwise, SIL is not 6 for the 4 and the 8. So hopefully that clears if else up. You can see we could have done that with case when. It just would have been like 4 extra characters of typing or something. So if you're comfortable with case when, you might as well use that. It's a little bit more clear, I think. But if else is kind of a handy shortcut, I guess. And if else is like a base R function that's been around for forever. So that's just kind of a nice thing to know. Questions about that? Okay. So there was a question about table with a Y, janitor table. So I kind of on the fly was showing you some adorning of the table, and I do want to get to like a real explanation on janitor, but because it's so useful and I keep bringing it up, figured I might as well show you a couple more examples here because that is just so good. So for this example, I'm using the penguins data set again, which is basically what I was doing in class. And so I showed you can use table to make not a cross table, not a 2x2 table, but a cross table because it's like a 3x3 table of species and sex. And sex has some missing values, so there's an NA column. And simple cross table with percent. So if we have here, we have counts, and I want to add, or not add, but replace those counts with the percents. And so I just use the default adorn percentages, but I pointed out that if you try to figure out what the denominator is, it looks like it's the row sum. So it's percent female within Adelaide. Penguins is 48%, and then it's 50% within Chinstrap and 46.7% within Gen 2. So these rows should add to 1. But you can change that. You can say, I want the denominator to actually be the column total. And so that means it's going to be within females, what's the percent of Gen 2 penguins? So now this column should add to 1. And so it's saying within females, 35% of them are Gen 2. Within your missing data, 45% of them are Gen 2. So it might be a preference on what you're trying to show. I'll show you another example in a second, but let's just run with that. So we have adorn percentages, the denominator is column. These columns should add to 1. And you can see like this is not 44 plus 0.44 plus 0.43 plus 0.54 is going to add to more than 1. And so that's exactly what happens when we add adorn totals. And I'm telling adorn totals, add a row total and a column total. Either you can choose that option, only show row totals or only show column totals, but I just want to show you both. And like I was saying, the columns sum to 1, but the rows sum to more than 1 or less than 1, and we end up with like 300% as our total, which is kind of weird. But we'll go with that for now. The other thing I showed you was adorn percent formatting, which instead of all these decimal points converts everything to a percentage number with a percent sign at the end of it, which I think looks a little nicer, especially for data presentation. And so again, now we have these 300%, but the insides of the table look nice. And one thing you need to notice that you have to have adorn totals before adding percent formatting, or else it's going to give you some error that it can't add them up. And that's because it's basically made them a character string. It's added percents. So adorn totals doesn't like that and wants to be put before adorn percent formatting. Table has a lot of this situation where it depends what order you put these functions. So read the help or play around with the ordering if you're getting some errors. And then the last thing I like to add in, if I have percent, sometimes I'll add back in the counts. But this time it puts the counts, the original counts we had, but they put it in parentheses. You can see our original table had 73, 73, and now we have 73, 73 here. And that's nice because you kind of get a sense of like how big your data really is. But I don't like this 100, 100, 300%. So what I would probably do in this situation is actually make my denominator from adorn percentages equal to all, because that's going to tell you what's the percent out of the total number of 344 penguins. It really depends what your question is, what your hypothesis is, and what you're trying to show. But in this situation where we want to show row and column totals, I think it makes more sense, because now our complete total is the denominator, so that's 100%. We can see that the overall there's 48% female, 48.8% male, 3.2% missing. We can see that then 44% of them are Adelaide, 19.8 chinstrap, and 36% Gen 2. And then we can see like this is one of the largest categories, right? Female Adelaide. If you're trying to compare like percents between species, you probably wouldn't want to use that kind of denominator. You need to basically pick one. Do you want to show rows, totals, and then use the column as the denominator, or do you want to show column totals and use the rows as the denominator? You just kind of have to play around with it and decide what message you're trying to send, I think. But just know that all of these have denominator and where options that tell you where the totals and where the percents come from. Okay, and then the last bonus thing I want to show you is, I don't think I made it to this part in part 5, but I wanted to show you GT. So GT is a package for making really nice HTML outputted tables. So you can see this output is nice, but it's not very pretty. And so GT is a simple way that has a simple function GT in there that will just make it look like a nice HTML table. So what I've done here is that was the same, this is the same as this, it's that code. I added a title, but I wanted to make it combined so that I could see it here. The placement is combined. If you don't put that, it tries to put sex on top of that column, and then GT doesn't work very well. But here we have GT just tacked onto the end of it, and that makes this nice table. And there are a lot of functions in GT. When we get to statistical summaries and statistical modeling, I'm going to show you a little bit more about this, but I wanted to give you just some examples. I just added a few kind of specialized functions that do nice things to your table here. So you can see the end result from adding these 3 functions. Basically, I added a header, and then I added a row name using row name column species. And then I added in the label species, I made it capital, and that put in this line in between species and the rest of it. And tab header is what made this header and subtitle, title and subtitle. And then tab spanner made this column header sex across those 3 columns. So this is just like a very quick introduction to GT. We'll talk about it more in depth later, but I want you to just be inspired to look more at this link, which has the intro kind of vignette that has a lot of good examples. So if you are trying to make a nice report, this is one way to really do that. So I think we'll probably get to that along with statistical summaries in like class 9 or 10, depending on how fast we go through stuff. How do you swap? Okay, I'll answer this one first. How do you swap so that the percents are in the, there is a way to do that, and I can't remember the name of the function. Has anyone else used this? I'll try to look it up in the break. Good question. There is a way to do that. And then another question is, in BSA 511, we use Cable. Cable is another package to make pretty tables. GT, I would say, is a lot more powerful. I used to use Cable for everything. I still use Cable a lot. I use a Cable and Cable Extra in combination. There's another package called Cable Extra. But Cable, I would say, is just very simplistic. You can't do a lot of this extra stuff. I'll show you an example in part 5, which is involving the summary tables and groupings, and you'll see that the default behavior of GT is just a little bit fancier than Cable, a little bit nicer. And let me just click on this. So you can see like obviously when you're publishing, publications have very specific, sometimes very specific restrictions on their tables. So GT tries to get toward that goal, and they have all of these aspects like a table's header, labels of groupings, footnotes, source notes. Cable has some of this, but it doesn't have everything. I would say GT is a little bit more flexible. And I'll try to show Cable too. Cable is built in with Knitr, so it's nice to just be able to use. Yeah, good question. GT is newer than Cable, so I think that's also probably why people often default to Cable, because we're used to using it. I'm trying to get better about using GT. There's also a package called GT Summary, which I showed you very briefly, I think in like class 1, which makes kind of like table 1s, like cohort descriptive tables. And I'm going to show you that again now that we know how to use some data wrangling functions, because that is kind of built on GT, but is used for summarizing data and models. Is really nice. All right. And okay, so some more examples. The muddiest points here are just a lot of bonus stuff. So I feel bad a little bit taking up time from class doing these, but I think they are useful and getting some more information on data wrangling that you're actually interested in. So I think it's worth the effort. So this question was about sorting and deduplicating prior to joining tables, and showing an example of how to do this to avoid the multiple key warning when merging tables. In class, whatever, I've lost, what is this, class 6, part 6. In part 6, I have an example where you do need to join 2 tables and you'll end up with duplicated keys, but it's actually a good thing. But sometimes it is a very bad thing. So for example, if you have a study cohort set and then you have longitudinal data and you want to join those, you're going to end up with multiple keys because you have multiple data points. But if you have duplicate keys in both your left and your right table, this can cause a lot of chaos. So here's a very simple example. So here's my left table. I'm going to call it example cohort. So I have Jane, Juan, Jessica, Jessica. Jessica is the same person. A, B, C, C. We can see that those last 2 values are duplicated. So we could use get dupes on that if we wanted. The other table I'm joining is example other, which has Juan, Juan, Jessica, and then 3 different values, Y. Let's just call it Y. So looking at that table, this is our left table and this is our right table. Jane is not in the right table. That's okay. Juan is in it twice. So if we have these duplicated rows, what happens if we join? So let's just left join. So that means I'm taking this left table, anytime I see a match from my key, which is going to be name in the right table, I attach it, I join it to the left table. So I'm going to end up with a Y value and pull it from this table, right? Match up those names and then pull out the Y. So this is the result. Jane didn't have any data in the right table, so she has a missing value of Y. Juan had 2 values in the right table and only 1 value in the left table. So what happened there? Juan got duplicated rows from the original left table and got both of their values, 3 and 1, from the right table. So was that what you expected? Maybe, maybe not. It's kind of kept all the data, that's good, but maybe that's not what we wanted. You have to be careful. And then Jessica had 2 identical values from the left table and then just 1 value from the right table, but because there were 2 in the left table, it still has 2 rows and I got 4 and 4 for the Y value. So maybe that's what you want, but probably not. So this is a side note of this, the way I joined. You notice I didn't mention the key because I knew that there was name and it was going to join by name. And so I was not worried about that, but you can specify by equals name or by equals name, just as a side note. If you need to specify the key, you should do it. Okay, so let's say that we realized that last row should not have been duplicated. So the one way to do that, to get rid of that last row, is to use the function distinct. And that will take only the distinct or unique rows from your data. So it's gotten rid of the duplicated rows. It's kind of like the flip side of get dupes, which we saw earlier today. And so let's join that. I used distinct on the first left table and then joined it with the right. So now we've gotten rid of those double Jessica rows. I only have one row for Jessica, but Juan still has the 2 rows. So the problem is that if we look at that cohort data, Juan in the other example, the right table has 2 different values for Y. So that could be on purpose. And maybe you want to keep that, but maybe it also was a typo. So let's just kind of assume that we actually only want to take one of those values. So going back down, what if we want to take the lowest Y value for each name? And that will allow us to only have 1 row per person, per name, and 1 Y value per name. So one way to do that is to say example other group by name and use this function slice min, which takes the minimum value within each grouping and keeps that. So now Juan only got the number 1 because the 3 was bigger than 1. So now we have kind of deduplicated the names from that table. So I'm joining my distinct cohort and my sliced other, and now we have a result that just has Jane, Juan, Jessica 1 time. So just a reminder, like that's a very specific example. It really depends on why there are duplicated keys. So you really have to think about what you want it to be doing. Oftentimes, just picking one, maybe you just want to pick like the earliest date. I think that's probably the most common thing is for me is getting data like from a lab and they have multiple lab values, but we really only want the one closest to the like baseline date, study entry date or whatever. So I would filter based on time since baseline and pick the one with the closest, the minimum value of days before a baseline. And that's how I would deduplicate that data, for example. So similar to what I did with the slice min. So yeah, it really depends on your specific case, but there are a lot of ways to deduplicate your data. And just as a side note, what happens in this scenario, going back to the original data frames, if we did a full join, if in this case, so a full join, if you remember, is joining and keeping both keeping all the keys from the left column and the left data set and the right data set. And in this case, it's exactly the same as left join because the left data set had all the keys in it. So that is the same. Inner join, on the other hand, only takes the keys or the names from that are in both tables. That means Jane got removed, but it is still keeping those doubles from the other 2. Any questions about that? We'll talk more about joining again when we get back to part 5. So, and there was a question, I answered this in Slack too, about saving graphics that we make in our homework, like using ggSave in a ping file or a glimpse, etc. And I'd say no, unless I specifically state save as a file, which you would then do with ggSave or like write Excel or write CSV or whatever. And save as an object, which is different, where we would save it within the R environment as a named object, like my plot or my summary, depending on the setting. And then there was an interesting question about information on primary data. And so I asked in Slack if anyone has more specifics on what they want to see with that. I would love to hear it, because to me, primary data could mean many, many, many things. And like what kind of research you're doing, what kind of data you see. Is it someone entering data and giving it to you? Is it an export from like a database system or an electronic health records capture system, or from a sequencing computer? So it could be many things. Today, we'll hopefully get started with working on a real data that I pulled from something that I've analyzed. It's still a subset of the data, and I had to kind of fake it so that I could share with you, but you'll get a sense of what the data usually looks like for me, which may be very different from what you might see or expect to see. And then I again pointed to these two paper. Well, I don't remember if I've shared this one before, but this was the one I think I made. Required reading is really good about data organization and spreadsheets. There's another article about how to share data for collaboration, which kind of goes a little bit more into like file types and so on. So both those are really useful to hear about what kind of the best way to share data with a statistician or an analyst. And the other point is that I wanted to be able to show you data cleaning and wrangling steps before we got to something that's like too messy. And so I think we're there, and I think we still need to talk a bit about how to handle dates and times and missing data, and we'll get there. We have a bit more about missing data today. But if you do have data or an idea of a data set you'd like me to go over in class, definitely let me know or describe like what your data might look like. And then there was a really good suggestion about showing kind of data that includes variables and measures that are kind of complicated in that they can be in many categories or like filled in, I guess. That harder to keep clean, but they are separate categories, such as sexual identity, race, ethnicity, disabilities. I haven't found a good public data set with those kind of variables that are not like super simplistic. So if anyone has a good idea about that, please send it my way. I'd say a lot of that data is probably in surveys or in electronic health records type data, which is inherently, well, very private and hard to get example data from. And so I'm still looking, but if you know something, let me know. The last muddy point was a question of something we haven't covered, but I wanted to show you the code or like have the code here in case you need it like right away or something. This question is, we have 100 CSVs to import, how to import data quickly. The best way that I would say is to use lists and per. We haven't talked about lists yet. We're going to talk about that after part 6. So part 7 will be on lists. Part per, which is a way to iterate over lists, we will talk about probably in the next class after that. We actually saw some lists today in some of the functions of the week. It's just another R data type that can be very useful. And so this code, I'm not going to go through it really, but I just want to say that the idea is you make a list of the names of your files that you want, and then you use per map to read _ CSV of all those files. Pretty simple, actually, once you have those tools. The idea, though, is that what are those 100 CSVs? Are they things that you're going to join together or stack together, like bind rows them all together? That part can be kind of tricky. If they all are like exactly tidy data sets in the same format, and you combine them, you just need that list, and then you say somewhere, I wrote that code. If you had 100 data that looked similar and were able to be bound together, all you would have to do is say bind rows of all that data, and you'd have one giant data frame. So when we talk about lists, I'll re-show this example, but if you want some like extra learning, you can go through that example, try it out on some of your files as well. All right, so just to point out that people in BSDA 511 have used summarizing group by a lot and joining. That's really good to know. Keep letting me know what you're learning in that class because it's changing every year, so it's hard to keep up. But I figured this year you would have learned a lot more R, so that's good. And today we're going to talk more about summarizing and joining. Messages. So there's kind of a request to hear more about how to deal with missing data, and we will talk about that in part 6 work hopefully today if I stop talking. And people like the challenges. Part 6, I will say I kind of maybe went overboard with the challenges, so we'll see how that goes. And we'll see how far we get. It might be next class when we go through that anyway. And the last message has to do with packages. So I will admit that I haven't been very good about kind of using precisely the packages that I need in class, just because I kind of use the same ones over and have you load them all just to make sure you have them all. And then maybe I randomly start using janitor during class and just so you have it loaded. But I think it is good practice to only load packages that you need, like in your homework or in an analysis. Though I will say I'm not very good about doing that. So it is a preferred method, but don't be like me and be careless about it. It doesn't change too much though. One thing to note, and I'm showing an example here, is if you have two packages that happen to use the same function name, that can cause problems. Someone asked about that in the beginning of class, like the beginning of the quarter. What happens if you have multiple packages that use the same name? And that can cause errors if you're expecting to use one function and you're getting another function. So just be careful about that. And that's another reason not to load too many extra packages that you don't need and aren't using. But what happens if that does happen and you need both those packages, for instance, which if you are doing a lot of omics analysis, this is probably going to happen to you at some point. Bioconductor has a lot of packages that use some function names that are in tidyverse. So if one of them being this bioconductor R package called annotation DBI. So annotation DBI has a select function. And you can imagine I'm always using my tidyverse tools and I'm always selecting. And then all of a sudden I try to use select and it's telling me, it's giving me a strange cryptic error when I know that it should be working. And that's usually a sign to me that I loaded annotation DBI after dplyr or tidyverse, and R is trying to use annotation DBI select and not dplyr select. So the way I usually get around it is either to make sure that I'm loading dplyr or tidyverse last. So I would say library annotation DBI, then library dplyr. Or if for some reason that I can't deal with that, I would load both of them. And then after all, these are all the messages that come out when I load packages. Just to show you, so this is the order I've loaded them. First dplyr, then annotation DBI. So this is all the messages about loading those two packages. I can ignore them, though it is kind of giving me a clue. The following objects are masked from dplyr: collapse, DSC, slice, as well as reduce, as well as select. So it's giving me a hint that some of these names are going to be different. So if I say select, if you type the name of a function in R without the parentheses, this is what it gives you. It gives you either the actual code for that function, or if it's a kind of a more complex package, it probably gives you some of these like standard generic blah, blah, blah stuff, which is like a masking of the true functions usage. But what the key here is that it says standard generic for select defined from package annotation DBI. But I want to use select from dplyr. So the way you really should do that is every time you select, put the package name and then double colon in front to tell R exactly what select you want to use. So I would do annotation DBI : select when I want to use that select function, or dplyr : select if I want to use the dplyr select function. But a kind of trick, if you don't anticipate using annotation DBI select function, you think that most of the time when you say select, you're going to want to use the dplyr one. You can redefine select by saying select assignment dplyr : select. And so now I'm telling R, every time I say select, I want to use the one from dplyr. Stop confusing that. And so now when I type select, it's telling me environment namespace dplyr, which means that it's using that function that I want. So this is kind of advanced thing because you haven't really gotten to a point where you're loading too many confusing packages, but at some point you probably will encounter something like this. So just pay attention to what order you're loading things. Also, it's truly good coding, like hygiene to actually specify the name of the package that you're using, so there's no confusion. But that does add a lot of extra text, so keep that in mind. Okay, so that was a lot. Maybe let's take a break and come back at like 4:30, and then we'll start part 5, or finish part 5, I guess. Okay. So going back to that question, back to the question about adorning ends, the way that you adorn ends, not in the parentheses, but in front, and then you put the parentheses in the percentages in the parentheses, is you use this argument, an adorn ends called position. And by default, position equals rear. Whereas if you want it to be switched, then you use position equals front. So that, yeah, I like that too. That looks nice, having the parentheses with your, why can't I say both those words? Percentages in your parentheses. It's also interesting to look at the arguments of this because you can change how your ends are stored and shown. So maybe you want something with like commas or 4K or scientific notation. If you have very high numbers, you can do that and create them and then add them in separately. So that's one way to do that, to kind of mutate your N and then put them in. And then also you can tell it which columns to adorn. Like maybe you only want female to have the parentheses or not. And there's some examples here, sort of funny way to use it, but yeah, it can be pretty powerful in the ways you can kind of like customize your janitor. All right. So I lost my chat. Hold on. Great. So last time, I think we got down to summarize, but we skipped the joining tables challenge. So I do kind of want you to have that kind of practice. This is going to be a practice with left join. In part 6, we have more joining practice, but I think it would be good to do this one. So if you don't remember, let's kind of go back. So we have our YRBSS data, which is the survey data, and we had stacked or bind rowsed all of the demographic data. And so when we got to joining tables and we talked about the different types of join, left join, right join, inner join, full join, most often I use left join or full join. We ended up with the demographic data, where I guess we haven't used YRBSS. We have our demographic data, and then we have the questions data. So let me just run this just as a reminder. If you wanna, if you're opening R and everything's blank, you can run all the chunks above a chunk by clicking on this little sideways play button or something. I don't know. So it's running everything, loading all my packages, making all my data. So you have YRBSS demo, which is the demographic data, and the questions data. Which has all the results of, well, a subset of the results of the survey questions. So let's have this little challenge of joining, just as kind of a refresher. How many of you are there? All right, well, for this one, I kind of tried to trip you up a little bit, mainly because if you noticed, record ID was the name of the record in one, and then here record was called record. So when you have different key names, you do have to specify which one matches up with which. And then year is also a matching key, and it's fine to join by year. I don't think you have to, because the records are unique. It's not like they're, oh no, I guess you do. Well, yeah, you do actually want, no, we don't have longitudinal data. I'm getting this confused with our next example. But in this example, like records are unique. It's not like you have multiple data points. So you really only need to join by record, but you could join by year as well if you wanted to. If you didn't specify year, I'm pretty sure it would make like another year column from the Y table from the right table, which you probably don't really want. So left join, this is your left table, your demographics. Your right table is the questions data, and that's how you join. So if we run this, and glimpse it, we can see now they're all together. All of the questions and the records and the demographic data are all together. We have some missing data, but that's okay. All right, any questions about that? Let's see. So we talked about summarize last time, but we didn't get quite through it. So if you remember, we'll come back to that join table in a little bit. If you remember, summarize condenses a big table into a summary measure. So you can either summarize across the whole table and make one value per the whole table. So whether that's mean or sum or median or min, you're just ignoring any groupings or anything. You're just collapsing it into that one summary statistic. And so we showed some examples of calculating the mean, standard deviation, year, mean, and you can calculate different functions in the same summarized statement. And I gave you a list of some sort of common functions. I was talking to one of you today. Sum is also useful. I might add that. And I'll show you a couple more examples, but first I want to show you that summarize is very powerful with group by. I guess we did talk about this last time. If you have a grouping or categorical variable, like in this case, for example, race or sex, maybe you want to group by that one of those categories and calculate summary statistics within those groupings. So that's where we use group by. So for example, here we're grouping by sex and we're calculating the mean within those values that we have for sex, which are female, male, and missing. And if we notice what happens when we group by something, it doesn't explicitly, when we just look at the data, it's sort of hard to tell, but there is a little bit of a sign here that says groups equals sex, but it doesn't really change the data too much other than adding that little extra tribute. It's more how you use the functions after you've grouped it. So once you've grouped it and then you use summarize, that's the powerful part about grouping. And so here we'll calculate both the mean and the standard deviation. I think we went through this last time. And so now we have two columns, mean age, SD age. And I did name those columns so that they're kind of meaningful to me. We can group by multiple groupings. So here we have grouped by sex and grade. And so within all the possible combinations of those groupings, we have mean and standard deviation of age here. And so again, just a reminder that this output is a tibble. It's showing you a tibble. And you can use it as such. So you can then mutate or arrange or plot it, use it in ggplot, etc. So that's a nice thing. We can save it as a data frame or tibble and use that later. I think I went over count last time, so I'm going to skip this a little bit because I want to get to across. So we used across with mutate, but we can also use across with summarize. So when we used across with mutate, we were mutating across multiple columns at the same time, implementing the same kind of mutating function on those columns. And here we're going to summarize across multiple columns at one time, summarizing with either the same function or multiple functions, like mean or median or whatever. So this is from challenge 2, just to make sure, which we already did, but I'll run this. So we have our complete data. And so I want to group by grade, and I want to take the mean of all of my numeric variables. So let's run this. And so this is useful in that we don't have to specify each column name. It just automatically calculates the mean of everything, though you do get some extra bonus things that are not that useful, like record ID happens to be a numeric value. Who cares what the mean of that is? You can, like I said, you could select on this. So maybe I'll get rid of that. I also don't really care about year. So let's just look at that. So now we can see that we have age num, BMI, weight, and grade num. And grade num is all missing. I wonder why, actually. Let's see what grade num is. It might be because, yeah, is missing. Oh, it's just missing at the top. That's right. Because that's, so if you remember, I didn't say this at the beginning of this class, but last class I mentioned that the question data is a subset of the cohort demographic data. So there are missing, some of these missing values are going to be because there wasn't survey data on them, I think. But we have like 12,000 people. So we'd have to kind of scroll through. Although actually, when I think about it, I don't remember why grade num. Maybe I didn't save that code or something. I'll have to check why that's all missing for all of these grades. That's telling me that because I did NA remove equals true and it's still giving me NA, that's telling me that it's actually missing in all of them. But it did work for the 3 other age, num, BMI, weight, kilograms. And we also got that row for the missing grade. And I think this is pretty powerful with numeric data. Sometimes it's useful for like character, categorical factor type data. So one way, I couldn't think of that many functions that I might use to summarize character data, but one might be n distinct. So n distinct is counting the number of distinct values for each value of the character vector. So let's summarize across all character vectors and use this function n distinct. And so we can see sex had 3 categories because it's counting missing, age had 8, and then some of these other kind of questionnaire data are categorical data. So ever smoked had 3 possible categories. So that might be useful if you see something unexpected, if you have more categories. So you can get that out of Skim. Skim also shows you that as well. But if you wanted to calculate it yourself, you could do that. Okay, so this is another challenge using across and summarize and group by. Some of this might be review for those of you who are very used to calculating summarize. But hopefully the cross function, getting some practice with that will be useful. So we want you to group by with summarize to calculate the minimum, maximum, and mean BMI by grade, and then by year. So those 2 should be pretty similar. And then calculate the number of distinct values of all columns that contain the word race. So that means essentially race 4 and race 5 within each group defined by sex. And then use that to plot, to build a box plot. So we talked a little bit about box plots last class. So make one with BMI as your y-axis, and then grade num on the x-axis, and fill mapped to sex, just so to see what that looks like. And I think I'll give you like 7-ish minutes for this one as well. If you don't finish it, that's okay. We'll talk about it in a little bit. So maybe let's come back at like 4:50 in about 8 minutes. Okay, you're all back. I'm guessing that wasn't enough time, but hopefully you at least got to some summarizing, which I just lost. Where'd it go? Okay, so are there any questions about any of this yet? No, okay. So this, well, actually, first of all, I should note that I realized why my grade num was missing, because last class I added this line where I wanted to also remove ND and show an example, but I actually had put grade here instead of grade num, which means I remade a grade num column and I removed ND, but that doesn't work because there's only THs in there. And then when I tried to make it numeric, then they were all set to missing. So my mistake made that weird. You might not have had that in your code, so you might not have had to deal with that, but I just remade my mutate grade num. Oh, and then I forgot to make it numeric. So I'm removing my TH from that, and then I'm making it numeric. So when I join and then I calculate that, now when I look at my table, I should have my grade num and grade, which is a character vector. So that I fixed that because I made that mistake up there. But that's not relevant really to this summarizing, because I didn't really ask about that. But you do, so this is challenge. Oops, yeah. So for the challenge, I asked you to summarize by grouping by grade num. Oh, it doesn't matter. I did ask about grade num. Well, you could have done it by grade. This is kind of the same idea. Group by grade or grade num, and then calculate the min BMI, max BMI, and mean BMI. And so I just specified those 3 functions, and I made sure to say NARM equals true because there is some missing data. And so if I run that, we can see I have a min column, mean column, max column for my 4 grades. And similarly, by year, I could do the same thing. Here I've added GT. Let me just do it here so we can see it. Just so you can see what the GT output looks like. It just makes it a little nicer table. Although you do get, because you have a lot of missing data in the first 4 years of the survey, they didn't take BMI as they didn't actually calculate BMI or like record it. And so those are missing. And so you get these kind of weird infinity and negative infinity because it's all missing. And so trying to calculate the minimum of an NAs, you get infinity. I don't know. That's a weird R thing. So it's odd. But then for the ones where there is data, you get this. So you could filter out those rows if you didn't like to look at that. And then the third one was kind of asking you to use across. You could have explicitly said across race 4 and race 7, but I used the tidy select verb starts with, which asks R to summarize across all columns that start with race. And I want to calculate the number of distinct values in that category, that column, grouped by grade. So let's run that. And we can see race 4 had 5 categories, which are the 4 race categories, and then NA. And then because race 7 has 7 race categories and NA, it has 8 distinct values. So kind of a silly calculation, but it is kind of a sanity check there. But we can also see that within each grade, there are people who have selected all the different race categories. Within each grade, there's not like anyone missing from any of those categories in any of the grades. And then I asked you to make a box plot. I mainly did this because I wanted to show you, I showed you box plots with faceting, I think last time, I don't remember. But I want to show you that if you'd use fill, it kind of does the same idea where you're comparing 2 groups, in this case, male and female, sex is male and female, and BMI is on the y-axis. So we're looking at distributions of BMI separated by sex and also by grade. So I haven't done any faceting, but I have essentially divided up the data into these 1, 2, 3, 4, 5 times 2, 10 categories. And I've looked at the distribution. So we can see like in 12th grade, BMI tended to be higher for males than on median, on average by the median, than in females. In the missing data, it just so happens that the male BMI was on average lower than the female BMI. This doesn't really show us how much data is within the missing category, for example. So that we would probably want to look at, but you can get a sense of the distributions across these categories. Any questions about that? Okay, the next part is my GT side note, which I kind of already did during the messy data, but I just want to show you what happens when I tack on GT to one of the summarized. Oh no, age num. Let's just calculate what. So I must have played around with my age num and messed it all up. So let me see. Let's find another. Let's just do BMI. Because who knows what I did. This is mostly just to show you what happens with GT. So run this. This mean age is going to be nonsensical, whatever. But I wanted to show you the default behavior for GT when you have a grouping is to make this kind of subheading. So this is the original table: female, grade num, and then mean imaginary BMI age, SD BMI, I should say. And because GT recognized that female was duplicated a bunch, male was duplicated a bunch, it makes this kind of little subheader grouping. So recognize that as a group by default, which I think is kind of nice. I think this looks a lot nicer than the default cable would have just, actually I can show you. I think I need the knitter package though for cable. cable, which is another way to make nice HTML tables, makes it look nice. It's printed nicely. It gives you nice text and everything. But I just kind of like the look of GT better. So that's just my preference in this case, because it made those cool groupings. Okay, so tangent about GT, but I do want to show a couple more kind of more advanced across examples. Don't worry if this is a little tricky. I'm kind of going from super simple to pretty hard. I'm going to show you the code, the full code first, and then kind of break it down why it works. So here, I want to calculate the proportion of people who selected the white race category. So I'm basically collapsing race both in the 4 category variable and the 7 category variable into white versus everybody else who selected any other category or missing. And the way to do that, the way I thought to do that, was to use mean of the true false statement that variable equals white, equals white, and remove my missing. And so I'll break that, why that works down in a second. But the idea is I take my data, I group by grade because I want to look at the proportion of white within each grade. I summarize across both race variables. And then my function for both is the mean of x equals white. And this little dot x is denoting the, that's the way you specify your custom function within a cross. You put a tilde in front of your function, and then wherever you want the value of that column to go, you put a dot x. Weird R formatting standards. I don't know. Sometimes it's a dot, sometimes it's a dot x. So that is confusing, I admit, but it's an R thing. So that's why we do it. And you can look at the help for a cross. It should tell us a little bit more about that. Functions. So this is our, it's showing an example here of using it the way. This is actually the functions argument. I could have specified that. So let's look at the output of this. Okay, so we can see that 10th, 11th, 12th, 9th are my categories, and it's telling me that 36% of kids in 10th grade identified as white race when they had the 4 race category, and approximately the same when it was the 7 race category, chose white. And it's kind of similar across grades. Though missing, it was a higher proportion of non-white and other race categories besides white in the missing grade. So that's sort of interesting. So why does that function work? I showed you, I think it was last time, a little bit more about using Booleans and turning that into a 0, 1, and then basically doing math on top of that. And that's what we're doing here. So let's take a little subset. So I've just taken race 4 from that data, and I've pulled out the first 10 values. So let's look at this, my race. So we can see it down here. So that's white, black, African-American, white, black, or African-American. We have 1 Hispanic, Latino, and number 10. And so we can see a good proportion of them have selected white. So this is my little test vector. Let's just count them up. We have 3 black or African Americans, 1 Hispanic, Latino, and 6 white, and it's the percentages. So we should get out, if this math works, we should get out 60%. So what this is doing is turning this test, my race equals white, into a Boolean statement. So we end up with true, false, true, true, etc. True when we have white, false when we don't. And the way we turned it into a 0, 1, we saw this 1 times my race equals white before, or like something equals something else. And so we can see that whenever we have a false and whenever we have a true, we get a 1. Whenever we have a false, we get a 0, and so on. Actually, let me put these together so you can see both. Yeah, so true, false, true, we get 1, 0, 1. And so doing this little trick of 1 times this gives us that numeric vector. That's the same exact thing as saying as dot numeric of that Boolean vector. So these are doing identical things. I tend to use this little shorthand when I'm trying to turn my binary variables into 0 and 1s, but you could also use this. But the idea is that now that it's numeric, I can use my numeric functions. I can take the sum of them which would be 6 out of the 10. And then I could also take the mean. And if we take the mean of a binary variable, that's the proportion. So the mean, if you're in biostats, you've probably had Bernoulli data and you've calculated proportions that way. It's the same idea. The mean of a 0, 1 variable is the proportion of ones in that data. So that's exactly what I'm doing, except I do have missing data. So I added my na.rm equals true. And so this is the function I'm using, except I replaced my race with .x because I'm using this generic function across both race categories, both race columns. So again, this is way more complicated than the simple examples I just showed you, but you can use your own functions. You can create your own functions within a cross, which makes this a super powerful way to summarize your data. And we'll have more, I have another example kind of like this in part 6 as well. So there's another example of using a custom function. This one is even more complicated, but I do this a lot. There's probably a much easier way to do this that I haven't figured out. So if anyone knows, let me know. But I like to do this where I know I have character data. I've gotten this data set. I can't look at all of it. Let's say I have a categorical variable and I know there should only be 3 categories, but I want to double check. So that's what I'm doing here is I'm checking each character vector and I'm looking at all the possible values of that character vector. So this is saying across my data, summarize across where is character. So all character columns. And then this function uses string flatten from the string.r package. And that essentially is a paste function. It pastes a bunch of values together. I'll show you in a second how that's used. And then I'm taking all the unique values and sorting them from that column, collapsing it by comma. So let's just run this so you can see what it does. So we can see in sex, now I have female, comma, male. So that has created a summary value that has the 2 levels. And I took out the missing. Age, got this, all the age values pasted together, grade, race, etc. I like to transpose this data because it's in very wide format and often you can't really see it. And then I make it a table and make all the row names moved over to a column named variable. So let me just actually run the transpose so you can see what it looks like. So transpose means turn your data, right? So before all of these were the column names, sex, age. It's hard to see because it's not a nice output. And then all of these were the values. And so if I make it a tibble and make GT on top of it, it makes the nicer printing. So it's a little easier to see. So I often print something like this for my data because sometimes I'll have something like female, male, and then I'll have comma male with lowercase m. Often things happen like this. So this will give me a red flag that there are unexpected values in my data. And it's just a way to kind of look at your data. You can't really, like you could get this if you made everything a factor and then skimmed it. That's another way to deal with this, but I kind of like doing it this way. It's just a little trick. So I want to go through this and why it works. So if we make a vector of my race 4 category, so this is my vec is just the full, I probably shouldn't have printed that out because it's like 12,000 rows. So it's a 12,000 length vector, all my race 4 categories. If I look just at the unique values, actually I could have used distinct, I think. Unique and distinct do this. No, because it's a character, whatever. Unique and distinct do similar things on data sets, maybe not on vectors. Unique tells me all the unique 1, 2, 3, 4, 5 categories of my vec. And then I sorted them because I just like to have them in order, a little easier to see. And string flatten was that string R function that I mentioned is kind of like paste, where it pastes things together, but it collapses them all into one long string. So let's just look at what string flatten does. By default, it puts them all together with no separation. It got rid of, like, it's not putting a space or anything in between in the categories. It's just making one long string out of that vector. So this was the original vector. The string flattens it, makes it one value. It's length 1. And so because I can't really read that as well, I put a little comma in between. So I'm telling it collapse with a comma. And so now I get all of their races: Black or African American, Hispanic, Latino, and white are my 4 categories from race 4. So this is the function I want to use. This like nested function. And then inside across, I need to put the tilde, and then wherever I have my vector, I put the dot x. And so that tells R that I want to use this function across the 2 race columns. I'm thinking of the other one, across all of the character columns. So it's using that same exact function to summarize my character vectors. And this works because it releases, or it results in a length 1 vector, right? It's created a summary statement. It's created a summary value of my data that has length 1. That's the one requirement for summarize, is that whatever function you use, mean, min, sum, string flatten, it needs to make 1 value. Otherwise, you're going to get an error that says R was expecting 1 value, it got whatever the length was. So just be careful with that. You can be really creative, but it has to come out with 1 value. Could we arrange the returns from string flatten? So do you mean arrange it after you flatten it? I don't think so. That's kind of why I sort before I flatten it, because I don't think once it's in the flatten, like I can even show you, I could just make random letters. And then if I string flatten that, it's just going to put it all together. It's hard to distinguish after you flattened it where the separations were and so on. So I would sort or like rearrange your string before you flatten it. Hopefully that answered your question. Any other questions about that? That is a very nested function. It's not very pretty, but I like to use it. And summarize is also, so we've talked about using summarize across multiple columns. I've shown you how to use multiple functions in the same summarize statement. You can also use multiple functions within across. So now we're getting like summarize across multiple columns and use multiple functions. So you can really automate your summarizing by doing this. So for example, suppose I want to summarize across these 2 columns, BMI and age num. This is my tidy select part, so I can select whatever set of columns I want using like starts with or where or whatever. Then when I have a function, I actually pass a list. So we haven't really talked about lists, but the idea is that you use this word list to create a list in R, and then you list out the names of your functions, or you could use the syntax like with the tilde and the dot x situation as well in within here if you want. And if these all have a common argument like na.rm equals true, you can pass that argument at the end after a comma, which just makes it a little cleaner. So let's just run this to see what happens. Oh, I don't have age num. Something wrong with my age num. I probably messed it up above. Let's use grade num. Okay, so BMI, BMI 1, BMI 2, BMI 3. That's not really very informative, but we can see that we have a min, a mean, and a max. We have a min, a mean, and a max for both. So if you wanted to make it a little more informative, you can name your functions. So that's what's happening here. Separate here. So the function argument now is the list, but it's really silly that you have to do this. I don't know why it doesn't do it automatically, but I name it min, mean, max. Actually, let's just make it a little more clear. Say I want to put capitals. because the left side is what I'm naming it and the right side is the name of the function that's built in. So you can see, time age num, having so many problems. Okay, grade num. And so you can see it's tacked on the name of the function as I called it to the column name. So that's nice because now you can tell what it's doing. So I could also have done this within a group, like by male, female. You could see where you could just go wild with across and summarize and get lots of output if you wanted. So that is an option. What's the difference? Oh yeah. So question is, what's the difference between list XYZ and CYZ XYZ? The list is a list of functions and not of vectors. Yeah, I wish we had gotten the list by now. Next, well, the way this is going, it'll be class, what are we at? It'll be class 8 probably where we start talking about lists. And I think in this situation, it is a list of functions. You can't really concatenate functions with a C or combine. C really is for vectors. A list is going to be allow basically a list. Hard to say anything else but list. But it's gonna make a list of different items that can be different item types. So I could have a list of data frames. I could have a list of vectors. I could have a list of functions. I could have a list of many different things. I'll show you just with numbers. So we'll talk all about lists. This is going to look really strange if you've never seen a list before, but this is what it looks like in R. It has separated out those 3 values, whereas C, 1, 2, 3 is just a vector. That's a data type, and a list is another data type. And it's taken 1 and put it as a length 1 vector in the first slot of the list, and then the second slot of the list is a 2, and the third is a 3. So it's kind of like, actually, I don't even know if this will work outside of, it does work, yeah, that's kind of cool. So list of 3 functions actually tells you that element 1 is a function, element 2 is a function, and element 3 is a function. So you could have any kind of data types in there. And generally, a lot of arguments call for a list, just because that's giving you more flexibility in what you can pass to that argument. I'm trying to think of another example we've seen. I'll try to think about that. When we talk about lists of data frames and how to manipulate that, you'll get a sense of how they can be powerful. Hopefully that helped. And you can see, let's see if we see the examples in across, if they have any good ones. Actually don't really, not here. No, you can kind of see it here. Here's one example in the help for summarize. And you can see there you're showing a mean and an SD list of functions. And they actually pass the names argument, which can change. So by default, the names is going to be the column name underscore name of the function, but you can actually specify that. Say I wanted to put in terms of like a separated by a dot. So you can see that. Yeah, so BMI.min, BMI.max. So that's what the dot names function argument does. Yeah, so you can really deep dive into all the different customizations here, but that's one way to really make summarize work well for you. Any other questions? Okay, so the last thing I want to talk about today, I don't think we'll start part 6, we'll just start it next week. I think that'll be better anyway, but I do want to get to pivoting. So probably those of you in 511 have seen pivoting because it is really useful for a lot of analysis situations. But the idea is that we have different, what we call shapes of data. So this is the difference between wide data and long data. We use those words a lot, especially when talking about like longitudinal data. which means repeated measures data or data over a certain time series. But another situation where this happens is actually in like genomics, omics, and transcriptomics type work. So if you're measuring gene expression, usually gene expression is going to be in the different way than we usually see it. So let me read in this example that we have. And we can see that usually when we have subject, human subject data or mouse data or whatever, the rows are observations on the subject, on the patient, on the mouse, and the columns are our variables. But in informatics, often it's flipped, transposed, kind of as we just did, where the TCGA 110 here is an ID of a person, or I don't remember exactly what this one is. I think it's just probably a sample, a tumor sample. And so we have these 4 observations. So these are our IDs of our subjects, and these are the gene names. So this is actually the name of the variables that we're measuring. And so whether or not it's flipped or not, it's not that useful for data manipulation because columns correspond to the samples. So we can't really plot different genes against each other because we have this transpose wide situation. So what we need is a single column that tells us all these values and then what gene that corresponds to. So looking at wide versus long, let's run this little GIF thing, GIF, whatever. So this is actually just an image. Let me make it bigger. So the idea is for wide data, you have your IDs, whatever they are, maybe their gene names or their subject names, whatever. So that's our 1 and 2. And then we have 3 columns, X, Y, Z. So this is wide data. Long data then turns that pivots, as we call it, into tidy data where we have an observation for each value. We have our IDs are now 1, 2, 1, 2, 1, 2 because X data for 1 and 2 are now in the key. X is our key, Y is our other key, Z is our other key. So the column names became our keys. And then the data inside of here then became our value. So we can see ID 1 key X value A was from this corner. And then the other X value B, which was for ID 2, is still right below it, but it's been separated out into this kind of key versus value matched pair. You can kind of think of this also if you have another example I have here is longitudinal data. So let's think about how, let's say you have ID 1 and ID 2 and X, Y, Z are measures taken at like time point 0, time point 1, time point 2. And so now key is actually time point. So X was 0, Y was 1, Z was 2. And then the value is the measurement taken at those times. So often we turn wide data into long when we want to be able to plot it or analyze it if we want to be able to say time is like a variable in our model, or key is a variable in our model in this case. And so we can see somewhere here. Okay, so pivot longer is what is the function we use to turn wide data into long data. So this is a little animation going from above, although this time there are 3, I know that's the same, X, Y, Z. It actually puts it in a little bit different order. So we can see the keys are drawn from the column names, X, Y, Z, and the values are drawn from the data. And so pivot wider takes some arguments that asks, first of all, what's the data? And that's the wide data. Second of all, what is your key going to be? Where are you getting the names? What are you going to call them? In this case, it's calling it key. Perhaps you want to call it time or variable name or whatever. I'll show you some examples. And then what do you want to call your values? Here it's calling it val for values, I guess. But you might also want to call it, it kind of depends, like, let's say you're taking BMI across 3 time points, you might want to call it BMI. So maybe your key is time and your value is BMI. and you've made it into long format where each row is a snapshot in time. So you can see you have a lot of duplicated IDs now. We have ID 1, 2 printed out 3 times because they had 3 keys and 3 values to put in a stack. And so pivot longer, I'd say, is probably the one that we use the most because as you'll see next week when we talk about plotting and what we need to get to a certain data format, often we pivot longer because we want to show all of those keys in one plot or in one analysis. And so we'll see some examples in a minute, but again, just to spell out those arguments, we have the columns, which are the columns to collapse. So you can imagine starting with this wide, maybe you have X, Y, Z, and then G, H, I to come up with the other letters. Some other data that you don't want to put in the long format. So you can specify a subset of your columns and not make all of your data long. And usually that is something you need to do. And that part, you can use the tidy select verb. So you could say, like, I want these 3 specific columns, X, Y, Z, or you could say across all numeric columns, etc. Or starts with all of those kind of tidy select names. And names too is the argument. You have to specify the name of the column where the labels will be consolidated to. Values too is going to be the name of the column where the data or the values from the wide data will be put. So in this example, let's again look at expression example. We have the column names are the sample names. So the tumor sample names. The gene symbol is our row, like ID, basically. And so all of these values are gene expression values. So P10 expression in this sample and in that sample and in that sample. And so I want to call my values, because that's exactly what it's measuring, is expression. And then I'm going to say my names are sample, because those are my sample IDs. And I don't really have to specify this because, well, I do have to specify this because I tell them what the key is. It's going to use the key as everything else that's not starts with TCGA. So I'm saying all of these 4 TCGA columns are the ones I'm going to pivot. So let's run that. I'm saving it as expression long. And so now we can see it's been pivoted where we have a sample ID expression was 4.1, and then all 4 P10s are now stacked on top of each other. This is exactly doing the exact same thing, just a different tidy selector. Instead of starts with, sometimes it's too hard to say that, like if they don't all start with something, or it's not easy to pick your other columns and you just have one key identifier. I often use calls equals negative that key name, because that's going to turn everything else except for basically your identifier, your key, and make it all pivoted. But this does the same thing because I'm saying every column except gene symbol. So either way, whichever makes more sense to you, you could use. So now that we have, why did we do this? Now that we have our long data, what can we do with this data? So now we have a categorical variable gene symbol, because we have however many it was, 4, I think, different genes. We have our data, we have our expression values. So I could make a box plot of expression and then group them essentially by gene symbol. So let's do that. And so we can see that MTOR expression is higher than KCN J9 expression and so on. We wouldn't have been able to do that with that original data because there was no value that, like, we couldn't group together the samples. The samples were separated by columns and not really by like data elements, or I guess that's how you say it. So that's a good reason to convert it to a long format. And so we could also make a heat map. I'm going to show another example of geomtile next week. But geomtile is another geometry that makes essentially a heat map. It creates you'll see a tiled plot where the color of the tile is a value of numeric value that you specify. So one thing that's going on here is that I've made gene symbol a factor and made it so that the levels are different order. So that's one reason to do a factor, make something a factor, because you can specify the plotting order. And so another, let me remove this just so you can see without factor reverse. So I've created a gene symbol, I made it a factor, I've made this ordering of factors, and you can see P10, mTOR, RKIP, probably not supposed to say it like that, but those genes are in this order. It starts from the bottom and then goes up. And this is our tile. And I filled the tile with log2 expression. That's pretty common in omics data, that you take the log2 transformation of your expression data just to make it a little more normally distributed. Geom tile makes the tile. You have to tell it what your X is, which are my samples. Y are my symbol names, gene symbol names. And then I've specified the fill. If I don't specify the fill, this is what it looks like. All one color. Didn't really like that. So I use the gradient where low is yellow, mid, where it's around 0 is white, and high is this purpley color. And so we can see that this sample has really low expression of KCNJ9. And then like this sample has high mTOR and P10 expression values. There's this factor reverse, FCT reverse, FCT rev, which all it does is reverse the level order. So sometimes the ordering, you don't want it to start from bottom to top, go from P10 all the way up to KC and J9. So this factor reverse is useful if you just want to flip it. So let's look at it now. And so now we have P10 at the top and KCN at the bottom. So that's just kind of a tip. We'll use that again in part 6 as well. Is it better to pivot your data before you join, or does it not matter? That likely you probably want to pivot before you join. But in theory, I'd say in most cases you could do either or. Like for instance, suppose we had cohort data on the left and longitudinal data on the right, and longitudinal data was in wide format. I could join those two together and then pivot, so it's now in long format. If I had pivoted first, we'll see an example next class of this, having long format data and joining it with a kind of regular sized cohort data. It does the same thing. You'll end up with the same result. So in most cases, it probably doesn't matter. I would probably pivot first, but I think that's a personal preference. There may be cases where it does matter though. I have to think about that. That's a good question. Yeah, you can always pivot later, I think. Probably. And so if there's any other questions? Another reason to make long data is maybe not what you would expect. So sometimes it doesn't seem like you have data in wide format. For instance, our YRBSS data, there's no longitudinal data, there's no weird transpose or anything. But suppose you have many numerical columns that you want to show on the same plot for whatever reason. So let's just look at YRBSS all. I want to make a bar plot. We haven't done GeoMBar yet, but GeoMBar is how you would make a bar plot, which essentially is like a count. I'll show you. Here it's counting all of the race 4. So it's telling me there are 4,000 people who selected white, 3,000 Hispanic, Latino, etc. So this is a bar plot. I want to make a bar plot of race 4. Sometimes you might just want to look at your data and make a bar plot of all of your categorical data. You could do that individually, make a bunch of separate bar plots and then paste them all together. That is one way. Or you could pivot. And so what I would do in this case is pivot longer first. I would pivot all of my character. Let's just, first thing I'm doing is converting everything to a factor. I think up above I converted some to a factor. So I'm just making everything a character just so I have consistent variable types across my categorical data. This isn't necessary if you don't have like mixed factors and characters, but I'm just making it all the same. So now I can say where is character, which means all of my character vectors. So those are the columns that I'm pivoting. I'm ignoring, for instance, year and record ID and BMI and all that. I want my names to be called variable name. It's kind of generic because I'm just taking all of my categorical variables. Values to value, also generic because they're measuring different things. So let's just see what happens here when I do that. So you can see all of my numeric data is here still. It's just been duplicated, just like all of my record IDs have now been duplicated across. So you can see this person has now many, many records. Actually, let's just view it because it's probably easier to see. Okay, so this is record ID. And you can see that my first sex, that person had male, for age 17 years old, grade, they were 12. So it's pulled all of my character data into the value column, and then it's identifying which column it came from in the variable name. And then it left all of my numeric data, which is fine because I don't really care about that right now. So I see that for each person, it's done that. And so now why is that useful? So let's just make a bar plot with that value as my kind of marker. So we can't really, it's all clumped together, but obviously this isn't what I want. It's just made, you can't see it, but every possible value, actually, let's just make a table of that. You can see what it's doing this way. So all of these, this is basically made a bar plot out of this table, right? It's checked, it's all of these possible values and then put the count by it. Not that useful, and you can't even see it. What I really want is to facet by my variable name. So let's add this facet wrap around the variable name. And you can see, essentially, it's separated now by characters. It's really hard to see because the font, I made it a big plot and the font is really small, but I'll read this to you. This says age, and it's created a bar plot of age. It's created a bar plot of age for smoked. It's created a bar plot of grade, but they're all kind of weirdly separated, and it's because it's kept every single possible value. It's alphabetized them. It's not that useful to have all those values in there. So what I need to do is actually say within the faceting, make the scale on the x-axis free to vary by category. So let's not make this so big because you can't really see it. You can look at that. So you can see now it looks a little bit normal. The labels are still kind of overlapping on each other and then look a little cramped, but you can kind of see like ever been bullied is this one is now only the variable, only the possibilities no, yes, NA. And then cigarettes 10, which we created up above, are these 4 categories. Some of them do look not good. They're really cramped together. So what I would actually do in this case is flip the axes. So I've specified earlier, I want my X to be value, but if I specify Y equals value, you can see it's a little easier to read. Sort of, except it's like probably really small on your guys' computers. So let me see, that makes it better. Kind of, so you can kind of see, you probably had to squint really hard. But age, now we have our age categories. And so it's not very pretty. It's hard to specify the ordering within all of these. It'd be really hard to do. But it is a nice way to just kind of get a snapshot of all of your variables and get a sense of the distribution there. And also all the possible values of those variables. And so one last customization thing I have, I think, is I didn't like that the NA values were showing up. So I filtered out my NA value just to make it a little bit easier to see. And then after that, I decided I want to compare male and female values. So what I did there was before I pivoted, I took out the sex column. Because if you think about it, if I want to make this bar plot have a male and female, I can't have sex as one of my original values because, well, I can actually, but it's easier to pull it out of pivot before I do that. So what I did was say all of my character values except sex, which then leaves sex as a category, which you can see here, and then does this pivoting across all the other variables and values and so on. So once I've done that, I have this new data set that I then show the exact same bar plot, except I used fill by sex. I added this one value, and I'm also still removing my missing variables. Other customizations I've made on this, I've just added the labeling, subtitles, I added a theme, facet wrap. I did have to, when I flipped my axes, I had to change it to scales free_y. Previously, I was doing free_x, excuse me. And then I told it I only want 3 columns just for kind of ease of viewing. So again, this is really tiny. Should have made it smaller. But you can see that color. Oops, there we go. Color now is by sex, so male, female, and then NA. So it gives you a little bit of a bird's eye view, I guess, of your data. And we'll see in next class some more examples of why you might want to pivot data that doesn't seem like it's in wide format, but long format makes it a lot easier to plot sometimes. All right, so that's the end of part 5, and I think we'll probably just stop here because I don't want to start part 6 and have to finish. So next week we'll go through part 6, which has a lot of data cleaning and more ggplots and some missing data, dealing with missing data. It's sort of like a challenge-filled way of dealing with, like, I'm using really messy data, giving you a lot of challenges to work on it on your own and kind of brainstorm how you would deal with it. So I think it's a good exercise in what we've learned. And then after that, we will start talking about lists and per and functions, which I think of as very important advanced R usage. So it's hard, but it's worth it when we learn how to use all that stuff. And last note is that pivot wider exists. We'll see a little bit of an example next week, and there is going to be an assignment. I haven't created it or finished creating it yet. I will try to put it up tomorrow in both the Dropbox and on Sakai and Slack, I guess. But I won't make it due till like next Sunday because I know you have your midterm still, and I don't want you to feel stressed about having homework as well. So, but you will have some practice dealing with all of this stuff. All right, thanks for sticking around. I'll see you all next week. Good luck. Let me know if you have questions on your midterm or anything.